the reaction kinetics and doing an iterative approach that way. In industry, commonly, high throughput combinatorial approaches are conducted, and this can be, it'll generate plenty of data, but a lot of data that has to be mined and fairly intensive. So what we're proposing at INL, at our Advanced Manufacturing Center, is what we call incremental kinetic synthesis, where it's, again, a cyclic iterative process where you do intrinsic kinetics with a temporal analysis of products instrument. And this was invented by John Gleaves, and he's currently working with us and preparing a tap reactor. And you can study very complex materials, actual working industrial catalysts this way. And then apply theory to the kinetic data generated. And Gregory Yablonsky is leading in this arena, coming up with different first principle theory of interpretation of the data. And the feedback loop is to then look at what do you need to change in the catalyst to get to the next step. So you can make very ultra sparse changes, submonolayer changes onto the catalyst surface, and then come back and conduct the experimental transformation. So we began collaborating back in year 2002 when I was at Roman Haas. Rebecca Fushimi was a graduate student at Washington University. John, of course, is a professor at Washington University. And under a Goalie grant, we studied the atomic tailoring of catalyst surfaces for high selectivity, partial oxidation of propane. So this work has been published, and we'll talk a little bit about it in the next few slides. So at that time, John Gleaves had the first generation tap reactor system, but did not have the methodology developed yet to add the submonolayer metal oxides onto the catalyst particles. So he and Rebecca developed a pulsed excimer laser ablation methodology to add in a very controlled manner certain amounts. In this case, we looked at palladium on silica first as a prototype, and then next took a commercial VPO catalyst and added submonolayer of copper and submonolayer of tellurium. And here's just a recap of what the tap can do for you. You can get a lot of, it's very informational rich. You can determine activation energies, number of active sites, surface concentrations, and really get a very fundamental understanding of the microkinetics, what's happening on the catalyst surface. And so we're able to conduct these type of experiments. Its advantages are you can run isothermally, so that if you're looking at exothermic reactions, you have good control there. You look at the intrinsic detailed kinetics. And essentially the catalyst is a small sandwich in between quartz particles that you locate in the small quartz tubular reactor system. So the molecules are really discretely defined and essentially undergo Knudsen transport. In this case, we're, as I mentioned earlier, we're looking at submonolayers of copper and tellurium on the VPO catalyst, and our reactant was 1-butene, our product furan, and through multiple pulsing, we were following the normalized yield of furan and seeing improvements with the submonolayer depositions of tellurium and copper with fairly good reproducibility. So where do we go from here? That was the GOLI grant conducted in the early 2000s, and what we're anticipating, the earlier system, the deposition was not fully integrated in with the tap, so one would have to do the deposition and transport the particles over to the tap reactor. But going forward, we'll be integrating it in a closed system under vacuum, and we're anticipating not only doing the metal atom source, but also having a capability of having nanoparticle addition to the catalyst particles, and which is shown here in this carousel. And then the particles can be transported over to the sample library and then undergo the TAP, temporal analysis of product analysis. So this system will be in the future being constructed. So how do we implement this in our advanced manufacturing? We're envisioning, again, a cyclic iterative process combining experiment with theory. And with the intrinsic kinetic properties, we will be able to gather the critical information of activity, selectivity, absorption constants, rate constants, and really understand individual discrete reaction steps to elucidate mechanistic pathways. And on the physical side of it, in the synthesis, we'll be able to add metals, mixed metal oxides, having these different deposition methodologies, and look at the different surface compositions, the interfacial areas, be able to titrate the number of active sites, and so forth. So it'll be very informational rich, and we feel that this is a more logical approach for doing catalysis and looking at very complex transformations. And a new design that's under consideration, we use, you saw earlier the laser ablation methodology. Next is anticipated a cathode sputtering mode where you could have different metal oxides available for the deposition onto the catalyst particles. So going forward, we're anticipating the arrival of the next state-of-the-art tap reactor. The system in the circle there, with the anticipation with future funding, will also incorporate the Surface Synthesis Center. And we're seeking collaborations with industry. We anticipate having a industrial consortium. We'll be having a workhouse and open consortium industrial workshop in October. We just founded the Center of Interface Reaction and Catalyst Engineering this month. And if you have time tonight, please stop by the poster session shown there, and you can learn more about the incremental kinetic synthesis, a new approach to complexity for industrial catalysts. And Dr. Fushimi will be there to present. So I joined INL in November, beginning of this year. We're establishing the Advanced Manufacturing Center, and we do many things in addition to what you've heard today. We're excellent at separation science, especially with lanthanides, and membrane technology, system engineering, and seek to help industry solve critical problems. We're also interacting with the Office of Science, seeking to do a very fundamental approach to catalyst design, and looking for ways to work with industry. We're very IP favorable, we believe, in terms of CRADAs. We recently formed in 2011 what we call the Center of Advanced Energy Sciences, and that's where we'll house our new tap reactor system, and looking for collaborations with academia and industry there. You can't see the lower line, but in 2016 getting funding for what we call the Manufacturing Development Center. So this will be a lot of possible piloting and scale-up of different technologies. And I guess I'm going a little bit fast here, but I'd like to thank my collaborators, Roger Song, who did much of the catalyst synthesis. He is recently retired from Nanotech, and Dr. Fushimi with our collaborations at Washington University, and now recently joining us at INL. Dr. Doug Buttry for the characterization work of the various mixed metal oxides that we mentioned today, and Dr. John Gleaves of Washington University. Thank you.
Thank you, Ann, for a very interesting lecture and for an early conclusion so we can have more discussions. There are no questions for the individual plenaries. There is coffee at a break available now. Again, go out to my right or left through the poster session. Thank you.